to Olivier. Olivier, if you're ready.
Yep.
Olivier joins us from Datatonic, and he was I think our second meetup, or second or third meetup speaker. So we're very privileged to have him come back to join us. I'm now filling for time as we play with voice mics. We good? Okay, great. So thank you. Hand over to Oliver.
Thank you. Hi everyone. I'm Oliver from Datatonic, and in this session I'm going to talk you a little bit through how we implement recommender systems in TensorFlow. A bit of introduction at Datatonic. We build big data analytics and machine learning solutions for clients across many industries. One of the sectors we work with a lot is e-commerce and retail, and together with these clients we build recommender systems that really try to personalize the experience that their users get. In the next 20 minutes or so, I'll give a little bit of introduction to recommender systems. Then I'll show you how this is put into action in TensorFlow, and then I'll also talk a bit about some recent advances in recommender systems. The good thing about introducing recommender systems is most people are actually really familiar with them already. Good examples are Netflix serving new films you might want to watch, Spotify's Weekly or Discover Weekly, or just product recommendations on many retail platforms. And there's a few more use cases that people don't usually realize it's a recommendation system. It's, for example, Google search. So if I put in Python into Google, this is what I get. And I imagine a lot of you get something very similar. But there's something a little bit wrong with it because it's heavily personalized. So if I want to look for the snake, I actually have to go to page 2. So even the search here is personalized, and that's most revenue generating when we look at ads. So the idea of the recommender system is obviously very simple. Given a user, I want to recommend a few products the user might have never interacted with, but that the system thinks the user will enjoy a lot. So how do we do that? Well, there's a very common approach called collaborative filtering, and it all boils a bit down to this matrix you see over here, where we have a few users and they interact with a few items, in this case books, and they might give out ratings, numbers between 1 and 4. You see this matrix is quite sparse because not everyone consumes all the items a platform has to offer. You literally physically can't do that. Or people just won't give ratings because you watch a film but you can't be bothered to. So the issue is we have a sparse matrix, and the problem actually becomes a matrix completion problem where I want to fill in these empty squares. If we would do that, then we could take a given user and just fill in these empty points for any items we want. We create a predicted rating, and then we just take the highest ratings and serve them as recommendations to the users because we're fairly confident that the user will enjoy that. So how are we going to do this? Well, one approach, collaborative filtering, will take this ratings matrix and factor it into 2 smaller matrices, one user-centric and one item-centric. And while it's doing that, it actually compresses them into a latent space. So we learned some kind of detached latent representations of the users and of the items. And then all we have to do to get back a prediction of a rating is we multiply this row, or take the dot product with a new item, and then we get the desired rating. In a bit more formal way, what we want to solve is this equation where we have a ratings matrix R, and we just want to do this factorization into x and y. We can learn this by minimizing the root mean squared error, and we can add some regularization if we'd like to, or add some biases as well to improve the score. This became very popular around 10 years ago through the Netflix prize, which was a very highly regarded and well-paid data science prize early on. And the solution was literally this, solved by SVD, single value decomposition. And this can be done actually really efficiently through alternating least squares, or also stochastic gradient descent. And many implementations are already there in Spark or other distributed systems to do this. So this is now a regression problem where we want to learn these ratings for every user. Is, for example, a number between 1 and 5. So now that we know a bit how we can do this, we want to find a good use case. And on today's occasion, I thought, what would be a better use case than actually trying to find love? And I'm sure Andy will really appreciate that today as well. So the idea here would be, can be based on, let's say, online dating data, find profiles that match each other really well through a recommender system approach. Well, to do that, we first need some data. Did a bit of research, and what I found was this Living SETI dataset from a Polish website. Not sure anyone here is registered here. They released the dataset in 2005 with around 70 million ratings. It contains about 140,000 active user profiles that give out ratings, so it's quite rich, but it's a bit dated. Interestingly, the website's still up. It still looks like this, probably like in 2005, and it has around 640 online users last time I checked. So let's dive a bit into the data set. As I said, we got these ratings. A user rates another profile, maybe based on the picture, a bit more information. And the ratings go from 1 to 10. We got a heavily predominated female data set, which is quite interesting, I think. 70% women. And if you look at the distribution, that's also quite peculiar, because we see a very high number of 10 ratings and a very high number of 1 ratings. And the ratio between female-male actually switches as well. So a lot of people actually just probably go, perfect 10 or a 1, and leave it like that. So probably not even the easiest distribution to learn for a model. So now that we have the data, and we know a bit how we can structure a recommender system and what equations we have to solve, we can put this into action. That's what everyone came here about, to learn how to do this in TensorFlow. And I want to take a minute or two to explain 2 more or less recent additions to TensorFlow. They were first in TensorFlow Contrib, but they matured into the core library, and that's the Dataset API and the Estimator API. So these high-level APIs really are designed to make the development of models easier, and maybe also the deployment, because it abstracts away a lot of the details you don't really want to know about as a user. What the dataset does is it lets you connect to some data sources on file, TF records, or cloud-based storage. And then it will also you can define pre-processing steps, batching, and all these things in a very reproducible way. And it will generate some iterator object that you define in the input function, and this is what plugs it into this estimator. And that's also something people are quite familiar with already if you use Keras or scikit-learn, where you usually have these classification wrappers, and all you do is put in the data reference and type .train or .fit. Estimator is pretty much the same thing. I add a model function, I add this input function, and then I just type .train, and I can include my metrics and package everything very neatly. Other really big benefit here is it makes it easier to deploy TensorFlow in a distributed way, or on new things like cloud TPUs, where there's already estimators, where you don't really have to deal with the hardware and how to create a graph and a session and iterate over that. That's all taken care of here. So very useful things. And at this point I also want to emphasize something, that TensorFlow is not just a framework for computer vision and NLP or time series, because most people think, we've got TensorFlow, it does deep learning, but it's more generally a numerical library for numerical computation, and it's going to be very useful because we can use an algorithm like this SVD type of matrix decomposition and easily put it into TensorFlow, and we're not restricted to more classical deep learning researches as the really great example we've seen previously, for example. So how are we going to do that? We first use the Dataset API to collect some data. We define this input function I mentioned. There's a bit of decoding and parsing the CSV, but then we can just build this text line data set. We can do things like shuffling. Important step here is that I apply this parse CSV function, but now this can be easily done in parallel. can do some caching, repeating as many epochs I want to train, and then at the end we just throw out an iterator object that the estimator function can train on. The nice thing here as well, this is really optimized. It uses the C++ queues under the hood, and you don't have to tweak or tune that in any way. With the input function, we can look a bit at the estimator now, where we actually already, let's say we have the model function already, we can collect this, we use the input function, but we define also our metrics up there, the training operations, where we feed in what kind of optimizer you want and how we train it, and then wrap it all up in this estimator object, and all that's left to do is really type .train or .evaluate. Well, let's get to the core. We've seen the loss function we want to optimize. So how do we do that? The upper part basically just describes how we translate the input, the data set we have, into representation that TensorFlow knows about. And this is tightly connected to the Dataset API. We can use things like the feature column to use categorical columns, things like that. And we do that on the user ID and the profile ID. And then we use this embedding column. And that's a really important point, because what this embedding does is it takes this categorical column, which will basically be one hot encoded, but it compresses it into a dense vector of a smaller dimension. And that's really what this matrix factorization approach is all about, that we kind of learn this latent space representation of the users and the items. And we use this trick here, these embeddings, they're actually equivalent to the factors people talk about in matrix factorization. And that's a really handy way to do this. To really map it to the TensorFlow model, we can use the input layer, and this puts out tensors. All right, now we got tensors, we're all familiar with that. So we got to reproduce the rating. So we do the dot product here, add some biases if you like, add some regularization, and then calculate the mean squared error. Here we are, this is the singular value decomposition, or an equivalent of in TensorFlow. This was basically the first step. Now we've done something and we know it that works really well, because systems and companies that run recommender systems have been using it for a decade. But there's way more to do. Because what we could also use is utilize the embeddings we already have, and now build a multi-layer perceptron, just a few feed-forward layers on top of that, and just train on that. But why would we want to throw away the matrix factorization we know is already a good tool? We don't have to. We can, on the side, run the same matrix factorization model we just saw, concatenate the top layer, and then train on that. This is basically an ensemble model of what we just saw previously, plus multi-layer perceptron. What's really cool now is that this MLP way allows us to easily add more information we might have. A bit of shortcoming of the matrix factorization approach is that we only put in user ID and an item ID. And if you have any metadata, let's say on the customers we have or the items we serve, this gets lost. And we need to find a more complex way to reintroduce that into a model. In TensorFlow, where we can flexibly write our layers and model architecture as we want, this is not an issue anymore, because we can embed this metadata. Again, as one hot encoded columns, numerical columns, more embeddings if you like, and include things like age, gender if you would have it. And the online dating data set I introduced actually has gender. Or if we would recommend films, like Netflix does, we might add the genre or film length. So here we can put in a bit more data and just concatenate this into this MLP. Seems a bit hand-wavy, we just add this to the concatenation, but as with many things in deep learning, it just works. So here are the results on this online dating data set. On the left is matrix factorization, the pure SVD approach. Get a root mean squared error 2.13. The MLP, pure MLP, just instead of doing the dot product, I add a few dense layers. That's a tiny bit better. But combining the both and adding the gender we have for each user really gets furthest. And I compared this to some research paper I found. The dataset is really not that common, and I only found this one research paper. And I can't say for sure they have exactly the same data, but we see we get ballpark something very similar or even better. Some training details are down there. It's really nothing too crazy. We just quickly applied this on this data set, but out of the box it already works really well. There was no hyperparameter optimization involved here. So this is how we would build a very simple recommender system in TensorFlow. And we can train this, we can train it and accelerate it on GPUs if you like, and we can obviously serve this through TensorFlow as well. But in the past few years, even decade, people evolved the field quite rapidly, and there's many new approaches, which we also tap in when we build recommender systems for our clients, because this simple approach gets you only so far. A few key points and ideas are, for example, implicit feedback. What we saw here is we have data with ratings, but it's not really what you usually experience, because quite often you only have interactions as in clicks or length of video watched, things like that. These are called implicit features, and explicit ratings are rather rare, because even if you have a framework that lets users provide these ratings, most users actually don't give them out. Learning implicit feedback can be done by replacing the ratings matrix we've seen before into an interaction matrix P, and then we add a confidence scalar C or matrix, and we can basically weight the implicit score we have to the confidence we think we can give to that. So we can both include, for example, number of clicks and number of or length of the video watched, and score or weight these differently. That became very popular. It is a very common approach now. Out of Spotify came actually this logistic factorization approach, where instead of minimizing the root mean squared error, we formulate the problem as a classification problem. And there's many actually combinations of the first 2 points where people really tune the loss function to optimize the problem. And what this allows you as well, if you tweak the loss function a little bit, you can easily up and down sample within the training and within TensorFlow, either through weighting or negative sampling, improving the recommender score further. So what we saw before as well, the results were done on an unsampled and unbiased data set, but people see a lot of improvements in scores if they introduce negative examples and so on. Furthermore, doesn't really add to training, but it definitely adds the evaluation, is looking beyond just classification or regression error and using metrics like the hit ratio or NDCG. What I want to show you now is 2 more approaches that are rather recent, I think a year or 2 ago. They both come out of Google, and they show a bit the state of the art of these deep recommender systems. What we see here is quite similar as what I trained the model on previously, where we have a deep model that's basically a multi-layer perceptron again. We find these embeddings, and we just add a wide model to the side, which is just a logistic regression model with a wide feature space. And we combine this in the same fashion, where we just have one output layer and we have a concatenation before. Google named this wide and deep. Idea is really we can have many continuous features as numeric columns and app installs, number of sessions, and then the user features, demographics, name of installed apps can be fed in as a categorical feature with embeddings. That's actually how Google Play Store serves recommended apps. And I'm not entirely sure whether this is still in place, but it definitely was used a few years ago. Another one is YouTube recommendations, also came out of Google. But you see this idea repeating itself, where we embed some feature vectors. It could be user or video specific, and we then build the MLP or any deep architecture on top of that. This model is actually rather complex. This is only the first step on how YouTube does it. It will be actually framed as an extreme multi-class classification, where the model outputs 1 million or so classes. And then there's a pretty smart box on top here where it does a nearest neighbor search and basically does a recommendation, and then uses some search indices to retrieve very relevant recommendations, and then feeds that into a second neural network, which does some fine-grained predictions as well. So this is how you can build off these simple ideas we saw previously, a few ensemble models, and then really stage this to something that can be tailored to your use case and to your data. That brings me to the takeaways. We saw that TensorFlow we can easily implement this SVD in a few lines. We can do much more than just computer vision or time series. The high-level APIs lets you reduce the number of lines you have to write quite dramatically, and it makes deployment or scaling out TensorFlow a lot easier as well. It's quite straightforward to implement custom algorithms or architectures, and then even swap out the loss functions and just really be creative with what you do in TensorFlow. And these embeddings plus hidden layer, multi-layer approach, it seems to be now almost a standard way to do things in deep recommender systems, but it just allows you to have a lot of freedom and really tailor your TensorFlow model to the data you've given and to the objective you want to maximize. That's it from my side. Thank you very much.
Nice. We can take a couple of questions. Does anyone have a question for Oliver? Yes, at the back. Yes.
So thank you very much for that. It's really like very traditional information.
Sorry, can I ask, can you give us your name and the company that you're from?
Oh yeah, I'm Anna and I work for HSBC and I'm actually working on a racist problem. So the question that I have for you is like, how do you take the time aspect and seasonality into account? For example, if you were to build something for news, where the freshness is quite important, but you still want to keep the personalization as well, how do you take that into account? And also the seasonality, so the fact that I happen to have a good day in the UK and I purchased a t-shirt doesn't necessarily mean that because I purchased that, I'm going to buy more t-shirts in a country where everywhere buildings.
Very good questions. The dataset here has no time features, so that's irrelevant. What we build for our clients sometimes includes that. The first step usually is just building some sort of histogram features or something that looks back in time, but that doesn't do very well at avoiding recent purchases. So either they will be solved on kind of business side where we know where we would output scores and then we know this has been previously bought, so we ignore this, like in a very rule-based fashion. But there's a lot of research into that area where people combine this with recurrent neural networks to get this time series aspect and to weight the recommendation accordingly. There's been great research done by Microsoft in that direction, really combining these two things to improve the timeliness of the problem.
That's what you would suggest, like to go down to the
It depends probably on the lengths, the time scales and the data that's available and all that, but it's definitely an option, yeah.
Yes.
Tom with CV Library. So I really liked all the approaches that you presented. And one thing that I was hoping that you might show, but you might not have time, was there will be profile texts of the male or female users on that website. So did you think of doing an embedding from that and doing any comparison based on?
That'd be very interesting. The data set I just found, I quickly searched, and this is what came up, and it really only had user ID, profile ID, rating, and gender. That's it. And I didn't do any web scraping. Obviously I couldn't link the profile ID to something real anyways. But I think that'd be very interesting. That's actually how, also part of the YouTube recommendations we just saw is YouTube uses the search tokens and then does some sort of tokenization, like an NLP problem, does embeddings on that, which actually is very much like word to back, and then uses that. So I think that would be a very valid approach. Yeah.
Cool, thanks.
Do you have any more? Yes, right here.
Hi, I'm Jan Kim now with two garden science, but that doesn't really matter that much. The question I have is, with all these feedbacks, like I think it was reflected in your dating website data as well as the feedback when I can say for myself, I only will ever give feedback if I'm really worked up about something, so there will be a bias in there. So is there any way to somehow factor that in?
Yeah, exactly this bias, yeah, either you give feedback if you're upset, if you don't like something, or if you like it very much. It's definitely a thing that's seen. I can't say that for sure. What we do is trial implicit feedback at times. I think other companies definitely moved away from explicit feedback. You've seen this with Netflix, like not even offering any rating anymore, because they probably found it's not as useful as you'd imagine. This implicit feedback with some weighting is probably the way to go around that, and there's many further approaches on top of that. So I think explicit feedback, if you really have a lot of data, like YouTube. So YouTube recommendations, as out of this paper, does not use thumb up or thumbs down. So they discard this even, because they probably know it's not very useful.